Welcome back. I thought I'd do a couple of centripetal acceleration problems, some of the more common ones that you maybe see in school. So let's say I have it could be a Hot Wheel or it could be a car, a real car, and let's say it's on a track. So let me draw the track. What's a good color for a track? I don't know. Yellow. It's a yellow track. So this is going to be a side view. And we all remember this from our Hot Wheel days, and the track does a loop-de-loop like that. And then I have a car, and let's say it's going at a constant velocity. We're not going to worry about the cars, or at least a constant speed, right? Because the direction of the velocity might change, just not the magnitude. So this is the car. And my question to you is, how fast does it have to be going? What's its speed have to be for it to not fall when it gets to this point in the loop-de-loop? So it's going to go like this. This is going to be the path of the car. How fast does it need to go? So let's just think about it. Of course, I have to give a little bit of information. Let's say the radius of this loop-de-loop. Let's say the radius of this loop-de-loop is, I don't know, let's say it's 20 feet. I'm making this up on the fly. I hope the numbers work out well. So what we have to figure out is essentially what is the centripetal acceleration going to be on this car. And if we know the centripetal acceleration, we know the radius, we can figure out the velocity. So let's just think about what happens to the car as it goes up the loop-de-loop. At this point, let's say when the car is right here, so this is the car, what is making the car's velocity change, right? Because at this point the car's velocity is like this, and then at this point the car's velocity is like this, at this point the car's velocity is like this. It's always going to be tangent to the loop-de-loop. Well, at this point, down here, it's actually going to be the normal force of the loop-de-loop. Right? As the car is kind of driving into the slope is putting upward pressure on the car that's making it go in the circular path. But as we go beyond this point, we see something interesting happening. There's going to be the normal force of the loop-de-loop itself, of the surface, and then we're also going to start having gravity pulling down on the car. And some portion of the gravity will kind of pull to the center. And it's a little complicated at this point. But at this point, let me draw the car. At this point, let me draw the upside down car. What are the forces? Well, if we want the car to just not fall, right, we'll have to, the only force is going to be the force of gravity, or the acceleration of gravity. If the car is going fast enough to offset the acceleration of gravity, then it'll stay on the loop-de-loop. So let's figure out how fast it has to be going to offset the acceleration of gravity. Well, we know from the previous video that the centripetal acceleration is equal to the magnitude. I'm going to put an absolute value around that, so it's not the velocity vector, it's the magnitude of the velocity. I know I keep changing conventions, but that's good for you because you'll see different things. Divided by the radius. Velocity squared over radius. And remember, this isn't the vector, this is just the magnitude. And once again, this is also just the magnitude of the acceleration vector. So we know what the acceleration vector is at this point. It's minus 32. Well, we're just worried about the magnitude, so we'll say it's 32 feet per second squared. That's the acceleration of gravity on the surface of the Earth at sea level. 30 feet per second squared, and that equals the velocity squared. I'll get rid of the absolute value sign, or the magnitude sign, divided by the radius, divided by 20. And so multiply both sides by 20, I get 640 is equal to velocity squared. And so 64 square root, 640 square root is 25.3. So the car has to be going 25.3 feet per second. So now I'll ask you a question. What happens if it's going at 20 feet per second? Well, if it's going at 20 feet per second, someplace around here, let me draw the path of a slower car going 20 feet per second. If the car's going 20 feet per second, it'll probably make it pretty far, and then someplace around here, it's just going to start falling, and then it'll fall down. That's a car going 20 feet per second. I'll do that in 20 feet per second. Now, there's another question. What's going to happen if the car goes faster? What happens if the velocity is, and I'll do it in a different color. What happens if the velocity is, I don't know, 50 feet per second? So this is a super fast car. Well, at this point, so if this was just a simple orbit problem, what would happen? We have this centripetal acceleration from gravity, but that alone isn't enough to offset its velocity. So if we have no other forces other than gravity, the car would kind of exit its orbit, you could kind of say, right? It would actually go out of its path. It might do something like this. Whoops, its path might look something like this. And I know I draw these very messy things, but it might actually fly out, right? So what's keeping it from flying out? Well, the actual surface of the loop-de-loop, right? So we have something very interesting going on here. If a car is going really fast, well, let's figure it out. What does the centripetal acceleration have to be? Well, if the car is going 50 feet per second, in order to keep it going in a circle, the acceleration has to be 50 squared over the radius, which is 20. 50 times 50, so that's 25 with 2 zeros over 20. One of the zeros cancel. So the acceleration is going to have to be 125 feet per second. The inward acceleration, the centripetal acceleration, has to be 125 feet per second. So what's going on? Gravity is only going to provide 32 feet per second of that. So the rest of it is actually going to be the normal force of the surface of the loop-de-loop, or of the surface of the road. Because the car is going to push, the car is going to want to kind of exit its orbit. It's going to want to do something like that. And what's keeping it from doing that is the road. The road is keeping the car contained. And so it's essentially putting enough extra force, enough extra normal force onto the car, and so that force will kind of, it'll be applied to the tires to offset that, and there you have it. And so think of it this way: if you were tied to the loop-de-loop on the inside right here, if this is some kind of Western movie where the heroine is about to die and there's a car coming that's going to roll her over. If that car is going at exactly 25.3 feet per second, it'll probably just kind of bump over the heroine. Actually, the heroine will probably cause the car to fall, and she probably won't die. But if that car is going at 50 feet per second, then there's enough normal force. So the road is pushing on the car, and of course there's an equal and opposite force, so the car is pushing down, and that amount that the car is pushing down would squish the heroine. So I don't know if that was disturbing or useful or confusing, but just another way to think about things. Anyway, I'll see you in the next video.